Hi, welcome. I'm Jeroen de Heert. I'm a program manager in Azure Data, and today I'm joined by my colleague Shreya. Hi.
Hey, Ron.
Hi. So the topic for today is the shortest path in graph databases. So first of all, what is a graph database?
Oh, good question. So let's quickly look at what is a graph database first. And a graph database is nothing but a collection of nodes and edges. Nodes represent your entities and edges represent your relationships.
Okay.
Right? So you may ask, how is it different from a relational database then, right? So the difference is that edges represent your many-to-many relationship. They can flexibly connect many node to many other node in the database, whereas a foreign key in a relational database can connect one entity type to many other entity types. So it represents one-to-many relationship. And then graph databases also support navigation through your graph, so easy query language for that. And they can do both OLTP and OLAP queries, just like relational databases. So we introduced native graph database features in SQL Server 2017. And with SQL Server 2017, you could create a graph, which was a collection of nodes and edges, node and edge tables. Again, node represented your entity and edges your relationship. And to support creation of these node and edge tables and to support navigation through your graph, we introduced DDL extensions and query language extensions.
Okay.
And that will help you through that. And there was a match built in that we introduced.
So that was 2017, right?
That was 2017.
Okay.
Right.
So what's new for 2019?
So in 2019, we have introduced some features. Let's go over what we have already introduced. And the topic for today, like you mentioned, is shortest path. So we'll go over that later in detail. So the first one is merge DML. This was specifically introduced to enable merging of edges scenario easier. Merge DML now supports match in the syntax. Using match in the syntax, match is basically a three-way join between node and edge tables.
Okay.
And if, let's say, in a graph, you want to insert a node, insert an edge only if it does not already exist between the two nodes, then you would use the merge DML and insert it only if it does not exist, and otherwise just update it, update the edge record. The other feature that we introduced was edge constraints. So in SQL Server 2017, an edge could connect any node to any other node in the database. With 2019, we have introduced edge constraints, which will help you define specific semantics on your edge table. So now you can say that a given edge only connects this particular type of node to this particular type of node in my graph, and nothing else is allowed to be connected using that edge. And you can also define cascading actions. So if a node is deleted, what happens to the connecting edge in that case? You can say it is deleted, and we'll automatically clean up the edges.
That's useful.
So there will be no dangling edges left behind.
Yeah, exactly. Yeah.
Right. And then other feature that we supported was view or derived table on nodes or edges. This is basically to support graph polymorphism type of queries. So you can now create a view or derived table on a collection of nodes or edges, and then use that view or derived table in the match class in your queries.
Okay.
So, but the topic for today, like you mentioned, is shortest path. So we are going to look at that feature. This we have just introduced with SQL Server 2019 CTP 3.1.
So, but I know I can use shortest path in typical networking scenarios, right? For example, if you do social networking, to find the distance between you and me on, let's say, LinkedIn or whatever, right?
Right, exactly.
But not everybody's in the business of networking. So what other kind of scenario do I use this as a customer?
Excellent question. So today I'm going to show you a demo of bill of materials or product hierarchy and how you can use shortest path there. So we created a graph database from AdventureWorks Bicycle Company bill of materials product hierarchy. And in the query that I'm going to demo here today, I'm going to show how you can find out if a product or part belongs to a given assembly or not, or what all assemblies it belongs to. So imagine you were the manufacturer and the owner of AdventureWorks bicycles, and you know that a bearing ball that you produce had some problems.
Right, I want to know.
In the production pipeline, right? So now you want to find out what all assemblies that bearing ball was used in, so that you can see the affected products. And if you have to recall those products, you can recall them, right? So to write that type of query, you can use this new shortest path function. And on the screen, you can see the query that can help you determine all the assemblies where bearing ball is used. So let's look at this query in detail. So we have this new function called shortest path, which you can use inside a match.
Okay.
It can be used only inside a match and only on graph, node, and edge tables.
Sure.
It takes a pattern as an input. It's a regular expression style pattern. So you go from one node to another node via edge. And this pattern, which is inside shortest path, where you defined plus outside it, this particular pattern, it just tells the engine that this is a pattern that will be repeated. It's a recursive pattern. So we'll keep traversing this pattern, this set of node and edges until we find the desired node.
So basically, that means that no matter how deep the edge, the graph database or the graph really is, we'll just keep searching till we find that bearing ball, wherever it is. And it doesn't matter how complex the product is that we built, right? If it's 10 levels deep, we'll find it.
Right, exactly.
Cool.
So this is what the plus here means. So in regular expression style syntax, plus means one or more repetition. So we'll go one or more times, and we'll keep going down the hierarchy until we find that particular product that we are looking for, right?
Awesome.
So now when you use the shortest path and you use these node and edges here with a regular expression, like I said, this particular pattern here, the shortest path pattern will be repeated recursively again and again. So anything coming out of this pattern or the output coming out of this will not just be your regular rows. It's a collection or a ordered set of edges and nodes that were traversed in that path to get to the particular product, right?
Sure.
So to tell the engine that this particular pattern has specific semantics, that there is a ordered collection of node and edges coming out from it, we use this for path syntax in the from clause to tell that these particular node and edge tables have specific semantics, special semantics. And along with that, when you cannot just select, because they are returning a collection. They are not just returning your rows, regular rows. So you cannot directly select like you select from a table.
No.
So to enable selecting from that collection or projecting particular attributes from that collection, we have supported aggregate functions. And you specify this within group graph path syntax along with the aggregate function, which tells the engine that this output is coming from a graph path. Right? And the supported aggregate functions with this first release are string ag, last value, min, max, sum, average, and count.
So string ag would just concatenate everything?
Yes, so string ag will concatenate in this particular example, it will concatenate the names of the products that were seen in the assembly line.
Right, so you would
to get to ball bearing.
So you would see the full path how we got to.
Exactly.
Cool.
Yeah, so let's look at a quick demo of this query. So this is the query that we saw there on the slides. We are trying to find out all the assemblies which have a bearing ball as one of the parts in their manufacturing pipeline or assembly line, right? So let's quickly run this. Like I mentioned, I've already set up a graph database in AdventureWorks. I created a product node and is part of Edge. So it's just a hierarchy of products. So here, if you can see, after I ran that query, it printed me all the assemblies which are using bearing ball, right? And it printed the entire path starting with bearing ball. So bearing ball is used in BB ball bearing assembly, which is used in this assembly, which is finally used for this particular bikes assembly.
So I get every single product and every sub product that uses that bearing ball.
Yes, exactly.
Cool.
Right. So we saw that there is this plus syntax, which lets you traverse multiple levels in the hierarchy. But what if you want to stop at a given level, right? So what if you want to say, find me anybody who is connected to me 1 to 3 hops away, like LinkedIn shows you, right? This person is connected to you by 3 hops, 3 indirections. So we have also supported using this in curly braces 1, n type of syntax. So next to your shortest path pattern, you can say that repeat this pattern recursively 1 to 3 hops. So what this means is it will find me all the assemblies where bearing ball is used, only 1 to 3 hops away. It will not traverse all the way up to the top.
Cool.
So let's quickly run this. And when we run it, we see that here's bearing ball, which is used in these assemblies, and the number of levels that I traverse to get to this is 1, 2, and 3.
1, 2, 3. Yeah.
So I used the count aggregate function here to get the number of levels that were traversed to get to a particular part.
Cool.
Right. And the third thing that I want to show here that you can do with shortest path is finding shortest path between two given nodes in the graph. So until now, the queries that we saw, we started from bearing ball and we kept traversing the graph until we exhausted it.
Yeah, right? We basically searched the whole thing.
Yes, so we basically found the shortest path starting from bearing ball to every other product that is in our pipeline, in our database.
Sure.
But now let's say if I want to find out the shortest path between bearing ball and a given bicycle, which has product ID 768. How do I do that? So I want to provide a terminating condition on the product also, right? So to do that, today you could have used the last value in the where clause and have provided a terminating condition on that. But last value is an aggregate function and you cannot use aggregate functions in the where clause today. So to do that, how you would do is you would write your shortest path query, put it inside a subquery, and then the outer query will have the filter on the final product. So this is how the query looks, and let's run this. And
so now we'll know for where in this one product the ball bearing is used.
So for this particular product,
right, exactly.
768, where bearing ball was whether bearing ball was used, and if it was used, how many levels down in the hierarchy.
Very cool.
Right. So, all right. So we saw 3 ways in which you can use shortest path today in this demo. And all these samples, all these queries that we saw and samples for other features are already uploaded on GitHub. So if viewers would like to download and play around with them, they can do that after the video.
Very cool. Well, that's a lot of cool stuff. Thanks a lot, Sriya.
Oh, yeah. Thank you. Thanks for having me here.
Sure. Our pleasure. So thanks also for watching, and please don't forget to like and subscribe, and see you next time.